Valerii Kravchuk. I'm a principal support engineer working for MariaDB Corporation, and today I'm going to speak about bpf trace as one of recent dynamic tracing tools that MySQL and MariaDB DBAs may use to study internals of servers, solve complex performance problems, and similar things. The subtitle says problems and solutions, so I'm going to show some subsets of performance problems that can be resolved with bpf trace, and also discuss how problematic is it to use it, why it's not so widely used, and how to resolve some of the dynamic tracing problems one may hit when using bpf trace. Few words about myself. I'm in this industry for basically 16 years. I worked for MySQL, Sun, Oracle, then joined Percona, then for last more than 5 years I am working for MariaDB Corporation. A long story short, in MariaDB I am trying to work on complex support issues, mostly performance related as much as possible. And since I've joined Percona, I'm also a public person. I have a blog with many posts related initially to bugs, but recently to solutions as well. Several how-tos. There is even a tag for bpf trace, a topic for today's talk there, so you can follow me. I have also a Twitter account and do all these kind of things in public. I like to speak about MySQL and MariaDB, mostly at FOSDEM and Percona Live conferences, but elsewhere as well. As I put it in short, I like to solve problems, and I do solve problems for our customers. And because of this long experience, I know a lot of people who deal with problems, customers, engineers, developers, and a lot of different ways to resolve the problems. So I really know things. Even though I work for MariaDB, I am not on a mission there from them here, so all views, ideas, and highlights and approaches are mine. They may not be shared by my current or previous employers or partners. Now back to the topic. Basically, there are several different sources to get the insights of what's going on inside MySQL or MariaDB server. Probably the oldest one, the original one that still would be preferred by many developers, is just to use debug binaries and debug package there that can let you enable and disable different parts of diagnostics output embedded into the server code here and there. There is a set of logs that is provided by MySQL server historically, a set of show commands. There are tables in the information schema. There is performance schema, after all, that was introduced in MySQL 5.5 many years ago with the eventual goal to be an ultimate solution to all performance wandering problems, as a source of all profiling information one can think about. Over these years, I had worked out my own habits on how to deal with complex performance problems, and they are based on the approach that requires use of the auth-level tracing and profiling tools available in the operating system at question. So it can be Linux in most cases, it can be Windows. Both of these operating systems, well, it can be IX as well. Any operating system should include and does include a set of tools created by its own developers to trace complex performance problems in the operating system kernels and system software to begin with. These can and should be applied to the applications as well. That's my point. There are different tools if we speak about Linux. There is, historically, they appeared in that order. There is a proc special file system where we can see the state of program execution of each process and thread, and all the files and kernel and memory and everything and whatnot as a set of files in a special file system. Soon after that, a very efficient dynamic tracing interface was added to Linux in kernels 2.6, called ftrace, function trace. It's an efficient way to enable debugging output dynamically without the need to change anything in the operating system and application code, unlike that debug binaries. You do not need any special binaries. On top of that, eventually, this framework was extended and additional events were added that are available via the perf sampling profiler originally. Later in kernels 4 mostly, a different system of dynamic tracing called eBPF, extended Berkeley packet filter, was added that allows actually to not only to trace things, but execute more or less arbitrary, but still verified and correct code in kernel context whenever some event happens. So it's not just print out, you can do basically everything. Then a set of tools was created based on that called BCC tools, bpf trace compiler collection tools. And one of the tools that was based on eBPF, but was aimed to become a more user-friendly and easier to use than BCC tools that require C and Python programming, basically, if not assembler for the virtual machine. It's called bpf trace, and it's a topic of today's talk. Besides that, there is a way to study what server does just by watching the traffic on the wire, TCP dump analysis. Ironically enough, BPF originally was created to improve and extend the way TCP dump works. So, what is this session basically about? It's about tracing, that is printing out something when something happens, and profiling, that is measuring something when something happens inside MySQL and MariaDB server code in production. What's important that I am going to speak about recent Linux kernel versions. All I say makes sense to use in kernels 5.x. And what I advocate here in this talk is for MySQL DBAs is to use a bpf-based bpf trace tools for all the one-time quick studies, testing, and for developing quite advanced utilities up to some level of complexity. Some of the problems are discussed, some of them are presented with solutions. What's most important in my performance studies and why I suggest to use source level tracing tool is main thing is the performance impact. All the older MySQL, even show commands, all the login, dtrace, debug binaries, whatever, they are hardly available in production because of their performance impact. Another thing that I am always trying to study any performance problems from both sides, from the application side and from the operating system and resource usage side. So with OS level tracing tools, I can apply the same instruments to study both sides of the problem. So that's why I am not speaking about performance schema to begin with, because while it's a quite efficient instrumentation of MySQL itself, it does not help with operating system, so you need still to study what happens inside the operating system. I also do not speak about performance schema because this topic is covered over the last more than 5 years in numerous talks. I'm not speaking about perf and BCC tools here specifically because bpf trace is somewhat easier to use for the DBA. It's more high level and very interesting and recent, so it's cool stuff. I'm basically suggesting to use Linux tracing tools, and of them bpf trace is good enough. Let me explain why by shamelessly exploiting this chart created by Brendan Gregg and shared at his site. So here we have a collection of Linux tracing and observability tools with the areas of the full application stack they apply to, from CPU performance counters to device drivers, network layer, system libraries, kernel interface, application itself. So what we can see on this chart is that there is a set of tools that cover the entire stack. bpf trace is the latest and one of them. There are others. If trace itself, perf, bpf trace of all of them may provide the smallest performance impact. and a lot of convenience. So that's why. Let's move on. As we speak about doing something or printing something when something occurs, what this something is, what events we can trace or what events we can use for our activities. They can be classified on 2 dimensions. First, this can be events in the kernel of the operating system or in the application, in the user space. Another dimension is, do we need to change something in the code of the kernel or application to have this event observable? So if we have, this is something developers should do explicitly, and it will be a kernel trace point in case of the kernel, and user-land statically defined tracing point in case of application. This USDT, also called dtrace probes, were popularized and actually invented and presented to wide use of application programmers by the dtrace dynamic tracing utility coming from Solaris initially. You can use dtrace these days in Linux as well, at least in Oracle Linux, but its time has gone. So bpftrace can do the same, but more. Of all these 4 different kind of events, I am mostly interested in user probes. That is, events that can be added dynamically to the application, in our case, MySQL Server, without any need for any change in the code anytime. That's because they are dynamic, and that's a big difference with the performance schema. If something is not instrumented in performance schema, you do not see it. If something is not instrumented by a trace points, for example, in the code of MySQL, nothing is instrumented right now. All the instrumentation points previously added were removed and not available in 8.0, for example. I can still add a user probe to every function and to almost every other line in the code by many tools, including bpftrace. So this is my main point of interest, but when I'm studying operating system side, I am interested in kernel probes and kernel trace points. Trace points, as they are already in the kernel code, form a kind of a stable, documented interface for tracing stuff. So they are usually preferred. But if we are brave enough, we can move on with automatic probes. So what eBPF brought to the picture? Previously, there were different systems. They were mentioned on that previous chart, like system tab, for example, where you can create a special kernel module that is called when some event happens. So there was a way, and there were different ways to do things in the kernel context and program what to do at the kernel context when some event happens. eBPF introduced a safe way to do this. So basically, eBPF is a lightweight language, assembler language at the lowest level, with libraries for C, Python, and whatever, Lua, binding. So there is a way to generate a code from a tiny virtual machine, LLVM if you care, that is run inside the Linux kernel in a safe way. How this happens? So the code for this virtual machine, architecture independent by the way, is first verified. Basic thing to check is if this probe is going to work correctly. That is it accessing the memory that is accessible for the user program, even theoretically? Is it accessing correct addresses? Is it even going to complete? Does it have infinite loops, for example? This is prevented. So only if the bytecode generating is safe, is going to complete and do not waste the kernel time, it's allowed to run on the machine. Moreover, this machine had got an interface to different events inside the kernel already pre-existing, like perf events for perf profiler or ftrace, tracing subsystem. So it allows actually to set all these kind of events and execute the code when this event happens. What the code can do? The code can output performance data. The code can maybe do asynchronous calls to the user land. And main thing that code is supposed to do is to collect and summarize the information in memory while working in the kernel context. This is working via so-called maps, BPF maps, that are basically associative arrays. So it's a set of values indexed by whatever arbitrary strings or even several strings, or multidimensional maps are also supported. So ideally, your eBPF program is collecting information, summarizing it as much as possible without the need to exchange it much with the user land, so without extra calls back in kernel context. And then when it's done, it shares the map with statistics collected to be read by the user program at a user land. Or it can just print things in the process as well. So it's up to you. eBPF interface and features evolved over time, starting from kernel 4.1. By the time of 4.9, it was quite complete. It allowed to trace everything that, for example, perf allows to trace as well. Moreover, it added some features to conveniently summarize the information in the maps in kernel memory. So the idea with everything in eBPF is the newer kernel you use, the better. Ideally, you need to use kernel 5 these days, but Ubuntu 18.0.4 is also good enough from this point of view in general for eBPF. For bpftrace, again, the newer the better. And actually, you, as it was visible from the previous chart, you cooperate with the eBPF system via some program, user program. You can write it yourself. You can use one of the existing ones. So the BPF compiler collection front ends in Python and Lua and whatever allowed users and engineers who work on kernel to create a set of tools, convenient command line tools that we can just use as DBAs. So you can check them here. By the way, in all my presentations that are visible in public, either at Percona site in this case, and in all cases at SlideShare, whenever you see a underlined word, you can click on it and end up at some source of additional information. So when I say recently, it means several years ago. From my point of view, the most convenient and easy to use front end, the program to generate BPF code, was added, called bpftrace. bpftrace is a front end with, I would say, interpreted, just-in-time compiled programming language, similar to AWK, that allows you to formulate your tracing and profiling needs as a set of basically pairs: probe, what is the event, and action. There is optional filter in between, so action can be conditional. It can be done only if some condition is true. As for probes, there are dozens of different probes you can use, at least a dozen. They can be classified as hardware probes, dynamic tracing in user land and in kernel context, tracing probes in the kernel, tracing probes in your application software, if any, software and hardware performance counters, special probes like profile and interval. Profile is for sampling profilers, interval is for executing some stuff every n seconds or milliseconds or whatever. And two special probes like those in AWK, begin and end. So in total, there is probably more than a dozen, a bit more is presented later. What we should do when working with bpftrace is, first of all, check the version. The newer version you use, the better. At this moment, you should better use at least 0.11. The one at this Ubuntu provided by the packages was 0.9.4 to all, so I had to build from source. So this is my version now. And the first thing to do next that you can do as normal user, not a super user, is to run help. Here it's explained with some highlights. So we start with usage. bpftrace can be used either with a file name that is supposed to be a BPF trace program, usually with the file extension of BT, but it does not matter. Or you can have a set of probes and actions, a program provided in the command line, or you can generate it elsewhere and provide it as a standard input. So these are three ways. There are several options that we can and should use. Of them, the most interesting are highlighted. When we speak specifically about kernel interface, many kernel functions do work with structures, not with basic types like integers. For example, 64-bit integer is the main data type supported by bpf trace. It can be interpreted as a string zero terminated, but basically it's all about 8-byte integers by default. So if you need something else, you have to define the structure. You can do it using the struct statement, similar to those structures used in C programming languages. But while you can define it at the moment in your own code, you can also use predefined headers from the Linux kernel or the application software, and you can provide a directory where they are located to do not care anymore about full path names, for example. Another option that is quite often used, there are literally dozens of thousands of trace points and user probes that you can define for the kernel, and you may not know the exact name of the probe. -L option allows you to search using patterns for probes that named like that. You can check the capabilities of your kernel with -info option. You can get more verbose output when the bpf trace program is processed with -v. You can involve unsafe functions and things like that. What is also widely used is -p and process ID of the process you are trying to monitor. It's a bit more complicated than just trace that process, but basically this is also often used. There are several environment variables that are important to set properly when you work with bpf trace. Of them, I would highlight these two bpf trace max keys in the map. So that associative arrays are limited in size because they are actually memory areas allocated inside the kernel context. So by default, you may have at most 4096 keys. You can redefine that and have more or less to define the performance impact and your needs. And another thing is the total number of probes in your program. It's limited to 512. You may need more at some stage. I'm not yet there. I defined maybe 10 probes at most. Another thing that recent versions, mine is quite recent, just like 10 days old, they allow to use C++ classes and class members without mangled names. If for some reason you do not need that, you can disable this feature. All the versions just do not support this stuff directly. So basically, the program consists of several triples like that, list of probes. You can define the same action for set of probes, optional filter, and action is a set of statements separated by a semicolon. Each probe has a different syntax. It can be as simple as just a word begin or end. It can be more complicated for user probes, for kernel probes, where you have to refer, for example, for user probe to the binary or library or whatever. I've added convenient links to the documentation of the bpf trace from GitHub, so you can study that in details. I will just provide a set of examples. Speaking about the other language constructs, so you've already seen that action is in curly braces and it's a block-based language like C, so they can be nested. Filter was also presented. If you care to comment your code, you can use single line comment and multi-line comments. Everything in between /*/ is a comment and is ignored. If you work with complicated, complex structures with many members, again, nested structures may be created with struct. You refer to struct members with dash larger such kind of an arrow, not a dot, but an arrow operator to refer to the structure member. You can use ternary operator logic. You can use logical condition if some condition, a block of action, else some block of action. You can use increments. Initially, the only way to repeat some action several times was the unroll construct of the language. It's better explained by example. This specific probe will print 1, 2, 3, 4, 5 at the beginning. This way, the body is executed 5 times. And here we care to specifically increment the counter, so each time we print something different. So there are associative arrays and square braces to access items in them. As I told you, everything basically is 8-byte integer signed 1. If you need some other integer, you can use cast. There is also a string function. You can cast to structures or whatever. Recent versions added a while loop, which is unsafe and experimental, but still can be used, C-style. You can stop working in the probe on current probe with return. There is exit function to stop executing program entirely. If we move to the variables, the most important part that we always use in BPF trace programs is built-in variables. Not those we define, but those that the tool conveniently provides without any definition, and they have a special meaning. So here we have mainly process ID, current thread ID, user and group ID for the process running, which CPU we run on, exact command binary that is executing, return value from the function, name of the probe, random value, C group that current process belongs to. Our functions that we trace may have arguments, and you refer to function arguments as arg0, arg1, argns starting from 0, like in C. So you need to know the code to refer to proper argument. If you refer to improper one that does not exist, or cast it in your own way, you will get a warning and compilation problem. The program will not run at all. There are convenient embedded variables for measuring time. It's elapsed time since we started BPF trace program, and n seconds, it's some timestamp that is like an absolute. There is a kernel stack and user stack, built-in variables and related functions that provide a bit more control, so that you can see where in the application you are now working, and what is the stack of kernel calls that is now working for your case if you made some system call. You can work with variables, user-defined variables. There are scratch ones starting with $. They are local to the probe. There are global ones, Scala. And in general, all the variables can be maps, so they can be associative arrays with one or more indexes. So you can, for example, have a variable named memory as associative array with 2 indexes, thread ID and user stack. So you are collecting a return value is the address of memory, for example, from malloc function that was allocated for this thread at this specific place in the code. Your BPF programs can also be parameterized. For example, for the same program to work with MySQL and MariaDB 10.5. In the first case, the binary name is MySQL D. In the second case, the binary name is MariaDB. And you still can parameterize it, and these positional parameters may be used in the context of the probe. There is a set, again, probably more than a dozen of built-in functions, so read the manual. Of them, I should mention printf, formatted print, similar to C. There is a convenient, easy-to-use print function that allows you to print maps, associative arrays entirely if you care. This is how you convert your 8-byte unsigned integer or signed integer, sorry, as a, let me get back, as a pointer to zero terminated string. It's a str function. You can preliminary stop executing of your program with exit. You can asynchronously execute some command at the user land with the system. You can print file context. You can find a lot of things. You can compare strings. Normally they compare with equal operator for filters, for example. But you can compare first n symbols of the string. You can find sizes of objects and structures and whatnot. So the list is a bit longer than we can see here. For the associative arrays, for maps, there is also a set of functions, some statistics, some for the entire array, average, minimum, maximal, statistics in one function. You can build histograms based on the map, so they can be linear or they can be logarithmical, so where the majority of the values hit of all the keys in this map. You can delete keys one by one. You can set entire set of keys to 0. You can clear everything and remove all the keys, and you can print the maps, basically. There are a bit more functions, but these are most important. So I suggest you to study the language in details based on its manual. Besides that, to start efficiently using bpftrace, you have to check at least simple commands other than just help. All other commands, by the way, will require you to run them as a sudo or as a root user. You can try elsewhere and you will see the related message. So if you do not know how to create a program, what event you may use, use -l. This should basically also work. For example, like that. -l trace point no, it does not work without root, even that simple stuff. So let's do it like that. Okay, have a syntax error. Probably I have to remove this stuff. Again, a syntax error. What I did wrong here. Okay. This sorry. Yes, so this is how it works. You can use star to match multiple different trace points. So these are a list of trace points in the kernel that starts with word right. And there are different classes of them. For each kind of a probe, there is a special, its own syntax. So here we can do something like print for the trace point subclass of syscalls, sysenter openet. That's when we open the file. So we print which command opened the file and which file is it. Here we access the file name member of the structure arguments. So here is the access operator, and we convert it to a zero terminated string. So it's printed as string according to printf. So here we can trace how many times specific binary is executed sysenter system call. Here we can collect the return values of the sysexit read system call and it's probably a numeric one, and build a histogram of where the majority of values come. You can find even more one-line examples here. So what's next? Next, if you get the code from GitHub like I did here, you can see that there is tools directory, and here you can find a lot of sample programs with documentation for them. I've highlighted just those I've usually use with a convenient extension of BT. So I suggest you to check how bigger programs than a couple of lines are usually written for the BPF trace. It will show you how to use built-in functions, what is the proper programming style and everything. I have a separate blog post about this kind of stuff. And to show you how it works, if you click on the link, you will end up at the blog post. This is how my presentations work. So let's take a quick look into the content of the biosnoop BT sample program. So it starts with a shebang line showing that you are going to execute the rest of the text with a BPF trace coming from your environment. So when I installed a newer version built from source, it was picked up just because it's the first in the path in the USR local bin. Then it's convenient including C style. If we want some header, we can include it. It would be a bit more complicated with MySQL headers because you usually may need many and they are too complex, but for Linux with a quite tiny and well-defined interface, it works. We need structures. Then we can see comments, somewhat shortened for the presentation purposes here, multi-line comment, then the begin probe. Begin probe is often used to show the usage of the program or to print out the header, so as it was in this case. Then we have two kernel probes. There are two kinds of programs actually working with kernel, depending on how the calls are executed. In some cases, you run kernel function and do something at the beginning and at return. So you may have a kret probe that like completes measuring something. Or you may have a pair of kernel functions, one starts something, another completes something. So it's called when something is done. Here we speak about block IO. And at the beginning, at IO start, we define several maps. At what moment we started, what process did that, what binary it was. And here we have a complicated structures with cast, and we pick up a disk name for block IO, like ABD1, for example. At your completion, we check it's also like a normal language construct to make sure that this had the previous matching starting call. So we make sure that the argument is not 0 and that the command that we work with when we hit this probe is already defined, it's not empty. So in the context of maps, if the value is not defined, it's 0 as a number and empty string as a string. So then we capture current moment of time and compute the difference of times. So how much time this disk block IO taken. Then we delete the keys from the map. So we do not want our map to become bigger over time. We print, so it's a tracing program. We print everything while we run. For tracing programs, usually the end probe is clearing the maps. Why? Because by default, BPF trace prints all the keys from every map that still exists automatically. Other way, when you do summarizing in some maps inside in the process and then just want to print statistics, the end probe may look like that. In the end probe, you actually print stuff, header, content of the map, and then you clear it so that it's not printed once again in an uncontrolled manner. So this is it. Now let's create some single line or a couple of lines BPF trace programs, and my usual first try with dynamic tracing and MySQL is try to capture query texts. on the while the query is running. I may have no space on disks for general query log. I may not have no way to capture queries on the wire, but I would like to understand which queries are coming. So for this, I need to know where in the code we can see the query text exactly. I know that in case of MariaDB 10.5, specifically taken for this example and for this blog post, this is visible in the dispatch command as a third argument that is called packet, as far as I remember, and it's actually SQL executed if it's normal SQL statement. So with this in mind, I can create a bpf trace program that will capture the queries and try to measure the execution time per query. So it's like a lightweight slow query log. So there are two probes. I start to measure time at the enter to the function, and at the end the query is actually done. So at return, I summarize, calculate the time spent and print some stuff, query and time spent for it. So how it works? uprobe works that way. The first argument is the binary. So I need a full path name to the binary. The second argument for the probe name is the function name. Here it's mangled. I used older version of bpf trace that was not working with the mangled name, so I have to do that. Where I got it from objdump, from for example, or just from some stack trace. There are different ways. So I am printing third argument, arg2, as a zero terminated string. I am storing it, sorry, in the map, and I am storing in another map for this thread ID a timestamp, and then I just compute difference and put it into milliseconds. So this is how it looks like. We can see that there are some extra output. So we see that this function is called without any text for the specific thread at the end. So that's something to clarify for a good program. And it runs forever, capturing all the queries until I press Ctrl+C, for example. It's a very simple way. So what else you can do? My next step usually is to create a kind of a profiler, or try to profile some load. And you can use bpf trace as a sampling profiler similar to perf. So for this, you have a profile probe. This probe has two additional arguments. Hertz, its frequency, it's always there, and how many samples per second you need. Hertz 99 in this case. Here I've added a filter. I'm interested in stacks only for MariaDB. And then I print user stack in so-called per format. By default, it prints in bpf trace own format. A bit different, but in any case, you will see stack frames, MySQL or MariaDB functions executed, starting from start thread. We use thread pool by default in 10.5, then do command, dispatch command. MySQL statement execute means it's prepared statement. No wonder I was using sysbench in the moment. See my blog post for way more details than you can imagine. So what else? You can use bpf trace to trace almost anything. I work closely with engineering teams and several people in engineering that work on performance problems either found by themselves or those our customers found. So in these dialogues, discussions, they often ask, do you know how to trace this or that? I'm saying probably yes, or probably no, but I will find out. And I am going to find out, and I did it for multiple tasks. In this case that was discussed in that blog post series, actually, or blog post like 3, the idea was to find out where mutex contention happened. And the first idea from the developer was to dynamically trace per thread mutex log calls. This is easy to do. The call comes from the library, libpthread. So here for the uprobe, I'm using library instead of MySQL D binary. The function name is pthread mutex log. And I can just see where we come to this call. From what stack and how many times. Unfortunately, we noticed two things. First thing, the performance impact of this collecting everything in the probe, not printing anything, but collecting and then printing at the end of the monitoring. It caused some notable, like 50% drop in performance for our sysbench test, unfortunately. Another thing that we noticed is calling pthread mutex log does not mean wait, because it always happens, even with wait or without wait. So we actually had to reconcentrate on waits. Then the developer gave me a hint, so you should actually trace LLL, low-level log wait with something. And I did it with bpf trace. I've tried to create a BT program inspired by those sample programs, so it was a complete program and it's shared in the blog. So it contains several probes. First of all, I used an argument. I decided to trace for n seconds. It passed as an argument so that I do not need to print at Ctrl+C, type it. So I have an interval probe. I have a U probe for LLL log wait, URED probe for LLL log wait. And what I capture, I start the moment when it started. I capture this stack. And at the end, I do this stuff. I compute the time spent inside. And in the map called futex stack, I collect this time for this specific stack for this specific thread. And then I print futex stack. I may have several items there. And then I delete everything for it to not be printed at the end of the programs. So the summarization of these prints, stack and time spent in it was done externally by AWK program. So I will not show you all the details. They in the blog. The performance impact was much smaller. So in this experimental way, we've had found out that it's not always beneficial for the performance to do everything in bpf trace program. Sometimes you have to rely on external userland programs and let userland do the job. Another thing, you can surely try to use bpf trace to trace any function call, but you should take a special care when you trace calls like LLL log wait or malloc that happens quite often. Again, because of performance impact. So you may be inspired by a simple one-liner like this. Here I can trace every malloc call for the MySQL G process, and I print which thread allocated how many bytes. It's quite convenient. You can create a test while this stuff is running. You can see, for example, how much memory is allocated per specific SQL in specific thread. So when I selected repeat 3 million times, I've got 3 million bytes and more allocated twice. So it's a good thing for tracing. But if I'm interested in finding out where the most of malloc calls happen in the code, or where the most of memory is allocated, or which memory allocated is not freed during the process of monitoring, so maybe it's a memory leak, you can build up on this simple tracing approach and try to capture everything and just, save the memory as I've shown for previously the example. This thread in this address had allocated the memory of this size, and when it's freed, we really delete the item from the map. It's this approach works, but it's a kind of lame, as I put it here, because again of the performance impact, unfortunately. If you're using the tool right, the performance impact is neglectable, though. I've made this test probably 2 years ago. One of the first tests of sysbench where I compared poor man profiler in the form of PMP capturing stacks once a second to perf, to bpf trace, and to executing without any tracing. So we can see that while GDB-based poor man's profiler makes things slow, that's expected, perf makes them almost as fast, bpf trace is the fastest. It's because of the amount of data written to the userland, it's the smallest. So twice times smaller amount of data, and it means faster writing of the data. So is bpf trace just a silver bullet that can resolve everything? Not actually. There are several problems with it. The main problem for many DBAs would be that you need a root sudo access even to list the probes, as we have seen. There is a problem of resource usage in the kernel context, so you should care about that. Same is actually true with performance schema and MySQL. If you try to capture more details, increase sizes of the buffer, there is a price, and this price is both in memory and in the negative effect of your instrumentation on performance. So it's nothing new. So there is like a technical problem that I had not yet tried to resolve in practice. While with perf, I was able to add dynamic probe to almost every other line in the code, and I can find these lines. Perf can show it traceable lines. I had never tried that with bpf trace, but it's doable. You can add address like offset from the beginning of the function, and you can compute these offsets with perf, for example. So that will surely work. Mangled names in C++ is mostly not a problem anymore in newer version. There I still suspect problem with virtual member functions in the complex class hierarchies. I hit it with perf and I expect it with bpf trace as well. bpf trace, by the way, may not be as good as perf in resolving names in stack traces, even if you provide symbolic information, because it does not parse ELF binary structure, so it's a bit weaker. You need recent kernel, surely, and you may have to build and install from source. I was really disappointed that on this Ubuntu to use majority of good bpf trace programs, I have to build from source. At Fedora 33, for example, I can rely on the package. And I have a limited real-life experience because customers do not have these latest kernels, and I am not good enough in making them install bpf trace, while GDB and perf are in a set of tools that majority of my customers already have installed. So all this stuff is not only something I work on, it's used. And when I decided to find out how much it's used by different vendors in MySQL community, I used my old trick of studying MySQL and friends by querying their public bugs databases. So I've queried in the Google bpf trace at public MySQL database, got 0 hits. Perf is quite popular. Same with Percona, 0 hits. Unfortunately, as I know, Percona does use bpf trace. They just do not show it in public bugs. And they found like 5 or 6 different hits for MariaDB. As I know that in recent years, like a couple of years, it's used. So I will just list several ideas and mention names. Daniel Black, a foundation developer and well-known community member in MySQL, suggests to use bpf trace. Yours truly suggests to use bpf trace for specific tasks. One of the key DB developers, a relatively new one, Eugen Kosov, does use bpf trace and suggests to use flame graphs. And Daniel Black even shared a kind of one-liner while studying one of the bugs. All these bugs are already fixed, and bpf trace plays some role there. So please do as the best of us. Marcos Albe from Percona had written several YouTube videos and made several sessions devoted to bpf trace. What's good about bpf trace? Sorry about that. bpf trace was good enough to solve performance problems in the Linux kernel itself, so it should be good enough for you as well. And as we speak about open source databases like MySQL or MariaDB, I see no good reasons not to use dynamic tracing, because you know the code, you can see it, you can study it. bpf trace is more convenient comparing to BCC compilers and easy to use for the DBA, more user-friendly tool. So I suggest to use it. If you hit any problems, performance problems, either you use bpf trace to explain it or not, please report it to the public bugs databases. Thank you very much, and thanks to Percona for letting me speak about bpf trace for more than 5 minutes. I am ready to answer your questions. Bye.